Magnetic resonance imaging is a method of creating images of internal organs in the human body accurately and without danger to the patient. Our presentation will be divided into 4 parts as shown in the figure. First, we start with the history and the development of MRI. In 1952, Dr. Bloch from Stanford University and Dr. Purcell from Harvard University were awarded the Nobel Prize for their work on what was then known as nuclear magnetic resonance, NMR. After 20 years, the word nuclear is substituted and it is now known as magnetic resonance imaging, MRI. In 1988, Dr. Damadian received the National Medal of Technology from President Reagan for his contributions to MRI. Since the 1980s, the world's first magnetic resonance imaging machine has appeared. Nowadays, there are about 22,000 machines in the world and over 60 million images taken from patients. Next, we will talk about the theoretical basis and how to create magnetic resonance images. The human body is a chemical composition of several elements, such as hydrogen, carbon, nitrogen, sodium, phosphorus, potassium, etc., in various chemical combinations. It has been observed that the atoms of some of these elements have odd number of protons in their nuclei, possess magnetic properties. The magnetic properties of the protons of these elements have been utilized to produce magnetic resonance signals and images. The most abundant of these present in the human body are the protons of hydrogen atom in the form of water and various other organic compounds such as fats, fluids, cholesterol. First, about the principle of operation, we talk about the concept of spin. Protons, neutrons, electrons and other particles possess a remarkable characteristic known as spin. They have a positive charge, and when they move, they produce an electric current and a magnetic field. Consequently, the proton can be compared to a little magnet. When not affected by the magnetic field, those spins rotate around the axis with random directions. The specific magnetic fields will interact and cancel each other. But when there is an external magnetic field, those spins will rearrange depending on the direction of the magnetic field. They will have a direction parallel or anti-parallel to the external magnetic field. Since the number of protons with an axis rotating in the same direction as the external magnetic field is always larger than the number of protons with an axis rotating in the opposite direction, the combined effect of the nuclei aligning with the external magnetic field produces magnetization according to the external magnetic field. This created net magnetization. The net magnetization increases as the external magnetic field strength B0 increases, or in other words, the net magnetization is proportional to the external magnetic field strength B0. The projection on the XYZ axis, then we have a longitudinal magnetization component and a transverse magnetization component. When placing the patient in a strong magnetic field, under the influence of the magnetic field, the protons with a longitudinal magnetization component parallel to the field line are low-energy protons. Protons with a longitudinal magnetization component in the opposite direction parallel to the magnetic field line are protons with a high energy level. However, these protons are not absolutely parallel but will rotate at a definite frequency determined by the LARMO equation. F equal to gamma multiply Bo over 2 pi. From the above relationship, we can see that the hydrogen isotope 1H has the largest Larmor constant gamma equals 42.58 MHz T. At the same time, hydro-1, with an odd number of protons, is an isotope with relatively high tissue concentration in most tissue types and highest sensitivity to magnetic resonance compared to other elements. Therefore, the 1H isotope is selected in the magnetic resonance imaging method. Next, we will introduce the working principle of magnetic resonance. Magnetic resonance is the phenomenon in which an atomic nucleus in a magnetic field absorbs or emits electromagnetic radiation. The protons in the test area of the body will change state if a source of radio waves or electromagnetic waves with a frequency equivalent to the frequency of protons released from a transmitter is applied. When magnetic resonance occurs, some atoms move from a low energy level to a high energy level. Their longitudinal magnetization component will shift to the opposite direction parallel to the external magnetic field, causing the change in total longitudinal magnetization will decrease and their transverse magnetization components will no longer cancel each other out but will add up to a total transverse magnetization component. When a radio frequency pulse is applied, some protons will reach a high energy level and their vectors become anti-parallel to the external magnetic field B0. Thus cancelling out the parallel vectors, thus causing longitudinal magnetization reduce. When the RF pulse is turned off, the protons are again influenced by the external magnetic field B0 and return to the direction in B0, meaning they return to a lower energy level. But it is not that the protons return to the B0 direction at the same time, but they change direction gradually and consecutively after the RF pulse is turned off, so the longitudinal magnetization component increases again to MO, and the process is called relaxation time. After the signal is obtained, through Fourier transform, magnetic resonance image is generated so that the doctor can diagnose, to determine the position of each slice, a magnetic field that varies according to the law of linear increase and decrease. This variable magnetic field is generated by the differential magnetic coils. The magnetic field generated by them will be added to the main magnetic field, and the total magnetic field acting on the body will be a magnetic field that varies linearly with space. Now we move on to what is consist of a MRI system, but first let's indicate about two MRI units. Digging deeper into the MRI system. 1. The magnet, which is a key element of the MRI system. It is integrated into the system, which also includes I, the RF, and E, gradient system. 2. Power supplies. 3. A computer system. 4. A documentation system. 5. Cooling system. 6. Monitoring camera. The main component of MRI is of course, the magnet. This is the most important and expensive component of the MRI system, which is available in three types. Permanent magnets. Though simple and cheap to run, they are still extremely heavy and do not generate high fields. Resistive systems. These are electromagnets wherein the magnetic field is generated by an electric current flowing through a coil. They have two major drawbacks, which are high electric and water consumption for cooling. Superconductive magnets. These are made of materials with no electric resistance when placed at a temperature close to absolute zero. They consume no power and allow stable and very high fields to be generated. Their major drawback is running costs of cryogens. There are three separated parts in the magnet. The first one is the coil. When the protons return to equilibrium, the signal is picked up by the receiver coil while the spins are stimulated by pulsed magnetic RF fields. These RF pulses are then transmitted. The resulting RF signal has to be received since it contains the information necessary for image reconstruction. The types of coils which being mentioned are the most commonly used: phased array coils, extremity coil, and NV array coil. The correct choice of a coil gives the best signal-to-noise ratio in the region of interest. Volume coils both transmit and receive radio frequency pulses and are specially called transceivers. Surface and local coils are traditionally used to improve the signal-to-noise ratio when imaging the structure near to the skin surface. They receive only signal. Phased array coils. It consists of multiple coils and receivers. It is used for larger areas. Magnetic shielding is required to protect the surrounding environment from the effects of fringe fields which surround a magnet. To maintain magnetic field homogeneity, shielding is necessary for the field to be protected from being distorted by the external environment. As a result, MRI systems generally require that the imaging room be shielded from external sources of RF energy. For most of the systems, this involves building RF shielding into the side walls, floor, and ceiling of the MRI site. RF shielding also prevents the RF signal generated during MRI measurements from being disturbed by radio signals outside the MRI room. Better homogeneity can also be achieved by electrical and mechanical adjustments by a process known as shimming. Inhomogeneities distort the spatial encoding, which in turn adversely affects the slice geometry. The MR image will show distortions in the slice plane. In order to prevent this type of image errors, the magnet system has to be adjusted during system installation to local conditions or deviations in unit spread prevailing in the unit. A process called shimming is used. We differentiate between active and passive shimming. In passive shimming, small iron plates are attached to the magnet. Their strategic placement compensates for inhomogeneities or distortions in the magnetic field. This may involve changing the configuration of the magnet or the addition of shim coils, active shimming, or small pieces of steel, passive shimming. The third component of a MRI magnet is the gradient coil. Gradient special coils vary the strength of the magnetic field, frequency, and phase of the electromagnetic wave in the transverse X and Y axes and longitudinal Z-axis planes. In order to get optimum image quality from a MRI system, a set of tests at regular interval along with the preventive maintenance measures are mandatory. The report of acceptance testing of the system, such as physical inventory, radio frequency shielding verification, cryogenic fluid consumption, magnetic field inhomogeneity, etc. All QA measures should be directed to get better image quality parameters. Also, the daily test ensures the smooth functioning of the system, avoiding inconvenience to the patient, which take only 20 minutes and are carried out by the technologist every morning before the patient examination is resumed. Prior to any examination being performed, the identity of the patient must be checked by the technologist. Patients arriving into MRI department are often worried or apprehensive, and this may make it difficult for them to understand the instructions or may produce an apparently aggressive attitude. In such cases, the technologist should convince amicably, and soft tone of voice often do a great deal of comfort and gives the patient confidence that he or she is in an efficient hand. Before entering the equipment room, the patient must wear a hospital gown and should remove all personal possessions. Wheelchair and trolleys which are MRI non-compatible must always be kept outside the magnet room. The patient is made to lie down on a table. This table then passes through a tunnel within the equipment. Inside, the tunnel is quite noisy when the scanning is going on. The region of interest is positioned at the center of the magnet. While the patient lies within the tunnel, images of the interested regions are taken from different angles. These images can be seen on a computer screen, and the entire procedure takes 30 to 45 minutes approximately, depending upon the strength of the magnetic field and the parameters set on. The following items can interfere with MRI and some can be hazardous to your safety. Please check if you have any of the following MRI incompatible objects: cardiac pacemaker lead wires, brain aneurysm clips, aortic clips, implanted neurostimulators or lead wires, artificial heart valve, insulin pump, electrodes and hearing aids. On the right is the figure where any metal inside of the body should be marked due to the need of hazardous precautions. Also, personal belongings such as those are being mentioned should be excludes: glasses, removable dental work, hearing aid, jewelry, watch, wallet or money clip, pens or pencils, keys, coins, pocket knife, metal zippers or buttons, belt buckle, shoes, magnetic strip cards, credit cards, bank cards, etc. Positioning of the patient can affect the safety of the scan procedure. Improper positioning can result in sunburn, like burns. In order to maintain a safer scan environment, the following precautions are to be taken. MRI systems are equipped with laser alignment lights. Exposing eyes to the laser alignment lights may result in eye injury. Do not stare directly into the laser beam. Place foams between the patient and the bore wherever a portion of the body comes in contact with the bore. Ensure that the patient does not touch the magnet bore. Orient the patient, head first or feet first, to minimize the length of the cable in the bore. For larger patients, use wide patient straps to secure the arms, preventing them from touching the bore. Thank you for your listening. Now is the time for the QA part.